All right, it is after 8 o'clock. I am going to get started on the material for the presentation. I am going to take a look at the chat in my upper window here. So if you guys see me glancing up during the presentation, I'll be kind of keeping an eye on the chat. I kind of wish there was an easy way that we could actually speak to one another, but somebody told me that you have to like go in and add temporary moderators, and I didn't feel like figuring it out. So I'll keep an eye on the chat while we're going. Derek has seen this presentation at least twice, and he's in the chat as well. So maybe he can pick up the slack on any questions that I don't see. So yeah, thanks everybody for coming to my, for me, 8 o'clock in the evening presentation on ludicrous ways to fix broken LabVIEW code. This is a presentation that I gave at GDevCon NA back in July, and I have edited it slightly since then. So yeah, let's go ahead and get started. Before I get into the material of the presentation, I want to point out that all of my presentations are available at this new website that I created recently called dnat.org. People were complaining to me that they're having trouble finding my stuff, so I created what I hope is a memorable URL. No more having to remember bit.ly/whatever. Just go to dnat.org, and all of my presentation content is available there, including this presentation we're doing right now. You will be able to find slides and demos and a link to a video recording of every one of my presentations there. So what am I going to talk about today? First of all, there are going to be some things in this presentation that need disclaimers at the beginning. Things like I'm going to be recommending you avoid features in LabVIEW. So I've got some disclaimers that I need to get out of the way at the beginning. And then I feel it's pertinent to give a brief autobiography of my relationship with LabVIEW. And the main part of the presentation is a Ludicrous play. Now, originally, that play had 10 acts, and in the spirit of distilling down my content, which Norm and I talked about this afternoon, I managed to whittle it down to 5 acts, and then I realized that one of the things I was going to talk about was going to make somebody at NI very sad because I was going to crap all over their features. So I didn't want to make that person sad, so I took that part out, and now we are left with a play of 4 acts and a prologue at the beginning. Now, first, my disclaimers. I rejoined the TSE organization at NI a couple of years ago. It used to be called AE, now it's called TSE, Technical Support Engineering. And in the time since I rejoined the team, I have seen a lot of broken LabVIEW code. And when I say broken LabVIEW code, I mean crashes when you run, hangs when you run, your exe won't build, you get compiler errors, all that kind of stuff. I've seen a lot of that. I mean, in the tech support organization, it kind of makes sense that I would see those kind of things. Now, I don't want somebody going home at the end of their workday and saying, man, today sucked because LabVIEW really screwed me over. I have had my fair share of those days, and I want to help people avoid getting stuck with LabVIEW. And so my number one goal when I am doing my job in TSE is to get LabVIEW programmers unstuck. Now, if possible, my number 2 goal is to get bugs reported. So if I can manage to get a hold of your code and submit a bug report, even if we got you some sort of workaround to get you moving, my number 2 goal is to still get those bugs sent over to R&D so that these things can get fixed. Now, in all this time in TSE, I have found some ludicrous ways to get people unstuck. Just complete nonsense how we managed to get this LabVIEW code to work. But there is a good chance that those of you who are watching this presentation right now will encounter situations similar to the ones I'm going to describe. And that's the reason I decided to give this presentation. I wanted to give y'all some tools in your tool belt to get unstuck in LabVIEW. So, but I mean, wouldn't it be better if we could avoid getting stuck in the first place? That's going to be the prologue of the presentation. Before I even get into the ludicrous stuff, I want to talk about some ways to avoid getting stuck in the first place. And as I mentioned at the beginning, in this presentation, I'm going to be saying, don't use this feature in LabVIEW or don't do this thing in LabVIEW. So these are my opinions based on the work I've done in tech support. This is not NI saying, don't use this feature. It's Darren saying, don't use this feature. Just want to make sure that's abundantly clear. Even though I am a representative of NI, I just want to, this isn't stuff that is the official word of the company. So I have a couple of wishes on this presentation. The first is that I really would like NI to prioritize editor and runtime performance and stability. I would like to see more prioritization of that kind of work. It's definitely being done. we're seeing bug fixes and improvements to performance and improvements to stability. I'd like to see more. I'd like to see that stuff prioritized very, very highly. So that's one of the reasons I'm putting all this information out there. And then for LabVIEW programmers like yourselves who are watching me, whenever you encounter the ludicrous situations I described in this presentation where you have some crazy workaround that gets you unstuck, please share your code with an I if you possibly can. Get a support request filed with an I. Here's my code. Here's the bug. There's this weird workaround that got me unstuck, but nevertheless, we can use that code to get bugs filed to LabVIEW R&D. All right, so let me give a brief autobiography with my relationship with LabVIEW. So back in 1998, I graduated from UT Austin with a mechanical engineering degree. I had zero programming experience. I did not do any programming in college. There was one lab where I clicked the run arrow on a LabVIEW 3.0 program. That was my experience with LabVIEW up until starting to work at NI. And I got a job at NI right out of school as we called them AEs at the time. We call them TSEs now, doing LabVIEW and DAC support. And my training for LabVIEW was Basics 1 and 2. That's what we called them back then. They're called Core 1, 2, and 3 now. But back then it was Basics 1 and 2. My first version of LabVIEW was version 5.01. So I have never known a LabVIEW without undo. And I feel relatively privileged because my LabVIEW friends who've been doing it longer than me have indicated that it was pretty painful to not have undo. So thankfully I had undo from the beginning, just barely. So yeah, almost 3 years later, so most of 99, 2000, 2001, I moved into LabVIEW R&D as a LabVIEW programmer, which is where I stayed for a really, really, really long time. If somebody was born the day that I moved to LabVIEW R&D, they would be able to vote the day I left LabVIEW R&D. I was there for over 18 years. And then in June of 2020, I moved basically back to the TSE group at NI as a LabVIEW expert and mentor for the newer engineers, helping train them, helping with more advanced LabVIEW escalations and things like that. So basically, I spent a couple of years supporting features of NI products. Then I spent 18 years developing features in NI products. And now I'm back to supporting NI products again. So in the past couple of years, as I've worked more in TSE, I have discovered that there are certain features in LabVIEW that if you use them, you should probably have NI support on speed dial because it is highly likely you're going to run into issues. Now, there are certain features of LabVIEW that I'm going to talk about that I think are non-essential features, but there are also features that are essential to large LabVIEW application development. And even though these features can be problematic and they can cause support issues, I feel like the ones I'm going to describe on this slide are essential features for large project development. First one is App Builder. You've got your code that you need to build into an EXE or a DLL or a source dist or whatever. You have to use App Builder. There's no way around it. And as a result, you have to use the project window, right? And you can't. There's no other place to put build specs in LabVIEW other than the project window. In my opinion, project libraries are essential for large LabVIEW application development, just in terms of the scoping and namespacing and code organization that they provide. Similarly, LabVIEW classes, I feel, are an essential feature for large LabVIEW application development. The encapsulation and dynamic dispatch, those are things that are essential for those large applications. And then finally, type definitions. I feel these 5 features here are essential to writing large LabVIEW apps. And so I'm not going to tell you not to use these. Even though App Builder, obviously, classes and type definitions together sometimes cause issues. The items on this slide are frequently involved in broken LabVIEW code, but I feel they're essential to doing large LabVIEW application development. But unfortunately, these essential features are very often used alongside non-essential LabVIEW features. So I have been back in the TSE group for 2.5 years now, and I have basically distilled down what LabVIEW features are most often associated with broken code and support issues. And there are 3 features in LabVIEW that are, in my opinion, non-essential to large application development, and yet we see them as support issues a disproportionate number of times. The first one of those features is X nodes. The next one of those features is malleable VIs. And PPLs are the most common non-essential LabVIEW feature that I see involved in broken code. My recommendation is to avoid these features whenever possible. Now, obviously, there are times we were even chatting before the presentation started about times when you kind of are stuck using some of these features. But if you can avoid these three things, avoid them, especially when they're used with each other or with LabVIEW classes or with type definitions. Now, the first one I mentioned was X nodes. Now, I'm going to imagine that there is at least one person attending this presentation right now who does not know what an X node is. So I'm going to do a quick little demo to sort of demonstrate what an X node is in case you've never ever heard of them before. All right, so before I demonstrate what an X node is, let's just talk about some of the basics of sort of built-in functions in LabVIEW, right? So I'm going to drop a sub-VI. This is the recursive file list sub-VI that ships with LabVIEW. And if we open its diagram, we can now see, obviously wires and terminals and functions and everything. And then, oh, look, here's another sub-VI. So let me go into its block diagram and look at it. And again, we have more functions and whatnot. At some point, we are going to get to the point in our code, and we are at this point here, where we cannot dig any further into this code. There are no more sub-VIs. There's no more items I can double click on because this block diagram is constructed entirely of built-in functions in the LabVIEW language. Sometimes, and those are typically colored light yellow, like you see them on the diagram here. And a lot of the times, LabVIEW programmers will use the term primitive to describe these built-in functions. And that basically means it is a core part of the language that you can't dig into any deeper. So we know what sub-VIs are, we know what primitives are. Well, the interesting thing is that there are some objects in LabVIEW that look like primitives, but really are not. For example, I'm going to drop the match regular expression function. So if you look at this function, you can see it certainly looks like a built-in function, right? It's got this, you can grow it and shrink it. If you show your context help, you can see the context help for it. So this function looks like a built-in primitive in the language. But this is an example of an X node, which is a way to write LabVIEW G code to mimic the behavior of a built-in function. Let me show you what I mean. If you have a built-in function, like let's say, I don't know, match pattern, because that's a built-in function. I can right-click on it and I can see the normal menus on this function. But if I right-click on this match regular expression function, there is a menu item that you don't normally see. Now, I have this menu in my LabVIEW because I have a hidden INI token that exposes X nodes. If you were to right-click on your match pattern function in your LabVIEW, you would not see this, but I see it because I have an INI token. And if I choose generated code, then I can now see the code behind that X node. So even though you thought that match regular expression function was a built-in primitive of the language, it really contains this LabVIEW code underneath it. Isn't that crazy? I'm imagining if you've never seen this before, this is probably very strange to you. But that is an example of an X node, all right? Now, I'll bet your first question, if you've never heard of these before, is what other things in LabVIEW are X nodes? That would have been my first question. Well, let's see. So I am going to go search in my VI lib of my LabVIEW for X node files, and we can see, oh my goodness, there are several X nodes in my LabVIEW. So if we just take a look at this list here, we can see the very first one is the database variant to data function is an X node. The error ring is an X node. There are several ExpressVI related items that are X nodes. Function blocks are X nodes. If we keep looking down the list, we can see a bunch of stuff with the storage VIs. If you look in the list, you'll see the timed loop there. The ears that are hanging off the sides of a timed loop, those are X nodes. And you can see match regular expression as well. So several things in the LabVIEW editor are X nodes. All right. Now, all that being said, X nodes have stability issues in LabVIEW, and they can cause problems. And for that reason, I recommend that you avoid X nodes. So match regular expression, for example, I do not use that function. I use match pattern. I find other things to use besides that X node. Now, there are some situations where there are no alternatives. For example, if you're doing LabVIEW FPGA programming, pretty much every FPGA node is actually an X node. So you have no alternative. You can't avoid X nodes if you're doing LabVIEW FPGA programming. There is a community of LabVIEW developers on lavag.org who write their own X nodes and share them with each other. I highly recommend you do not do that, because it is very likely that the X node you write that does some cool, nifty little thing is not going to be generally usable in your entire app. There's going to be some bug or some problem with it. So I highly recommend you avoid writing your own X nodes for that reason. And once PPLs get involved, if you're doing PPLs and X nodes, the chances that you're going to have problems increase exponentially. So we're going to come back and revisit X nodes later, but that's kind of my intro. If you'd never heard of them before, I probably just blew your minds. But that is a feature in LabVIEW that seems on the surface like it'd be really cool, but actually, in my opinion, causes more trouble than it's worth. All right, so now let's move on to malleable VIs. So again, let me do a quick demo if you've never seen malleable VIs before. So my favorite malleable VI is remove duplicates from 1D array. So we've got this VI here, and we can see that it has an array of variants as an input and an array of variants as an output. And the VI, if we look at its context help, basically tells us exactly what its name tells us. It removes duplicates from 1D array. So I'm going to make an array of strings, and I'm going to wire it into this VI. And I'm going to make an array of, paths and wire that into this VI. And maybe I'll make an array of error clusters and wire that into this VI. Notice that the VI can take anything. And as long as it is a 1D array, this will take an 1D array of anything. I see a quick question on the chat about the video being available. You can actually watch right now. This is already recorded. If you go to dnat.org, you'll see a link to this presentation. And at that link, there's a YouTube video already that we made from GDevCon NA. So yeah, that's already available. But yeah, moving on. So this is an example of a malleable VI. So if we look at the diagram of this malleable VI, we can see that it looks like a normal VI. It's got a control input. It's got an indicator input. But if we look at its file extension on disk, we see that it is a .vim file and not a .vi file. That's literally all you need to do in LabVIEW to make something a malleable VI is just save it with a .vim extension. And once you do that, your VI will be able to do this really cool functionality where it adapts to whatever data type is wired in. And so yeah, we see that this is what the source malleable VI looks like. If we then go look at one of the particular instances, we can see, oh, it's the same thing, only it got turned into the array of error clusters instead of the array of variants. So that is a malleable VI. And they sound pretty freaking cool, don't they? Well, they are actually pretty freaking cool. And if you've got really simple malleable VIs, I think those are probably fine to use. You can see a couple of simple ones here. We've got remove duplicates from 1D array, again, one of my favorites. We've got a malleable VI that will turn an enum into an array of enums where that array contains every enum value that's in the source enum. So for simple things like this, I think malleable VIs are great. When they have problems is when they start doing more complex things, particularly if you have malleable VIs that are keying off of LabVIEW class terminals. And especially if you then take those malleable VIs and build them into PPLs, as we mentioned before, combining some of those problematic features. One of the most common issues with malleable VIs is just your stuff randomly breaks, and it can be super frustrating. I recently worked on a very large project that another developer had written, thousands of VIs, and I had not worked on this project before. And so I pulled down his code from Git. And this was all source only code. So I had to, when I opened his project, all the VIs had to compile. And this project with thousands of VIs, which is perfectly runnable on my colleague's computer, everything's busted on my computer. So I start digging into this code. And again, the .vi files are identical. I pulled them from Git, from his submission, right? There's no changes. But just with he used a bunch of malleable VIs. And what I had to do was delete broken wires and then recreate the exact same wire. And all of a sudden it's no longer broken. Or delete a malleable VI off of the block diagram and then drop exactly the same malleable VI on the block diagram and wire up to it, and all of a sudden stuff's not broken. It's frustrating. And if we can avoid malleable VIs, then we can avoid some of these problems. And in my opinion, I'd rather have a clunkier API, an API that's got like multiple instances that I've created that I have to, pick one to wire to, as opposed to the elegance of malleable VIs, but then they cause me build issues later on. So that's the reason I recommend with malleable VIs. The simple ones are probably okay. I would avoid using them for any more, and I know I'm being kind of vague here by saying more complex, but definitely once you start throwing class terminals on a malleable VI conpain, that's a good example of something that will very likely cause you build issues, recompile issues as those malleable VIs get more complex. And then finally, the feature that is easily the #1 most frequently occurring LabVIEW feature in escalations that I've helped with in the TSE group over the past couple of years is PPLs. If you have a single LV lib, and that LV lib optionally includes a single LV class, PPLs are probably okay in that situation. But that almost never happens. Like most PPLs I see have, a library with multiple classes in it with overrides. And in those cases, my recommendation is to avoid using those. Now, one possible alternative is LLBs. Now, people think I'm joking when I say that. I'm totally not joking. PPLs, one of the reasons we like them is because they offer really fast load time of groups of VIs. They are, in fact, a PPL is the fastest way to load a group of VIs into memory in LabVIEW. But you know what the second fastest way is? LLBs. So if there's any way that now I'm not saying you should store your source code in LLBs. Store your source code as separate VIs in Git. Make a source distribution of your code and build into an LLB instead of a PPL if possible. Really quick, I see a question in the chat. Shouldn't R&D just work on malleable VIs? Absolutely. Malleable VIs are more stable now than they were when they first came out. I have not yet been convinced that they are stable enough that I would feel comfortable using them in those complex use cases that I mentioned. Yeah, Derek basically mentions here, R&D fixes the bugs when we get them, and they're fixing the bugs. And someday I would love for this presentation, instead of having 4 acts, to have 0 acts and no prologue. I would love for this presentation to go away. But we've got these issues that I see coming into the support group at NI, so I'm going to talk to you guys about the ludicrous ways we can fix them until I don't need to talk about that anymore. But yeah, coming back to PPLs, if you absolutely insist on using them, and again, I recognize that there are use cases where people still choose to use them. I do have a few pieces of guidance. One is make sure there are no X nodes in your source library, because again, X nodes and PPLs together, bad news. Try not to use PPLs alongside malleable VIs. Again, combination of these features. And I know it's difficult, but if there's any way that you can, if you're going to use PPLs, not have classes inside those PPLs, that's another way to avoid one of these vectors. And then, so I have a suggestion. If you're going to use PPLs, your life will be so much easier if you always build and install your PPLs to the exact same location. Again, assuming a single platform. If you've got a PPL distributing across multiple targets, that's not going to work. But same platform, always just install your PPLs to C:/PPLs. Build them there, install them there. Maybe stick your company name on there, C:/mycompany PPLs, whatever. But always pick one spot on your disk, and it should be very close to the root of your C drive. And if your builds of your PPLs always go there, and if your installs of your PPLs always go in that same spot, then I think that's going to help you avoid a lot of possible issues with PPLs and linking. Now, my colleague who's in the chat, Derek, he wrote a couple of articles on ni.com for solving some common PPL issues having to do with builds and search dialogues and namespacing. Definitely take a look at those articles if you're moving in the direction of PPLs and you run into some of these issues. All right, that was a long prologue. It is time for me to get into the 4 acts of my ludicrous play. And Act 1 is when LabVIEW features you love break your heart. Now, to start off this act, I'm going to share a not so famous LabVIEW quote from history. The error ring is fantastic. I love this feature. That is a quote from yours truly about, back at NI Week 2018, so a few years back. when I gave my presentation on what to expect when you're expecting an error. I have a link for that down there at the bottom of the slide. But yeah, I was a big fan of the error ring for a long, long time. And we're about to hear a story about why that may not be the case anymore. So this is a case study of a bug report that came to me while I was working in TSE. A LabVIEW programmer, whenever he does Control F in a VI, LabVIEW would crash. This only happened to him in a new release of LabVIEW. At the time, LabVIEW 2021 SP1 had just come out and he was getting this crash. He had not seen it in previous versions. Now, here's where things start to get interesting. The crash would only happen if the active framework PPL was loaded in the project. What's the active framework PPL? Well, we'll get into that. But so far, we've got two features on my list. One of them is an essential feature, which is classes. One of them is an unessential feature, which is PPLs. So we've got two features that we know could cause problems. So on the Homeland Security Advisory System, I'd say right now we are at an elevated risk of LabVIEW attacks. So we need to keep our eyes peeled. If you see something, say something. We've got PPLs and classes together. Let's keep an eye on that, all right? So here's the problem though. I could not reproduce this issue. I built my active framework into a PPL. My Control F just worked fine. So I talked to the LabVIEW programmer a little bit more, and he told me, oh wait, well I'm not using the active framework as it ships with LabVIEW. I've actually got a modified active framework that I'm using. I said, oh really? How is it modified? And he sent me a link to a page on ni.com that told you how to modify your active framework in a certain way. Specifically, his modified AF is, it takes certain parts of active framework that are not part of the active framework library, moves them into the active framework library, and then builds the PPL. I didn't even know people did that. I didn't even know there were parts of active framework that weren't part of the active framework library. Maybe at one point I did and I forgot. Well, R&D discovered that after all of this, there was a corrupt VI in the modified active framework PPL. So let me switch over to LabVIEW and kind of show what I'm talking about. So let's drop a VI like launch nested actor. So this is one of the core VIs in active framework. And if we look at it, we see that it is a member of active framework.lvlib, active framework.lv class, launch nested actor. Okay, so this VI is part of active framework.lvlib. Well, it turns out, as I mentioned in the slides, there are parts of active framework that are not part of the active framework lvlib. So for example, send message and wait for response is part of the active framework API. But look, reply message LV class, send a message and wait for response. Where's active framework.lvlib? It's not there. This is an example of an active framework piece that is not part of the active framework lvlib. So that's what I was talking about. There's this modified procedure to go mess with active framework lvlib, move this kind of stuff into it, and then build the PPL. So yeah, once we found that out, we talked to R&D. R&D looked at the modified active framework PPL. Once you add all that stuff into it, and they said, oh well, there's a corrupt VI in this PPL, and that's what's causing Control F to crash. And I said, okay, well, what's the corrupt VI that y'all are finding? And they said, oh, it's reply message do.vi. So I looked at this VI and I opened its block diagram. And I thought, well, this is a pretty simple looking VI. We're just doing an enqueue and we've got this sub VI that's probably not doing much. How would this VI become corrupted when it got built into a PPL? And that's when I got a little worried when I saw this error case structure here, because when we look in the other frame, oh no, there's an error ring there. An error ring is an X node. Are y'all curious what the generated code for an error ring looks like? Well, it's kind of a letdown because it's not that interesting. It's a big old string constant wire to error cluster from errorcode.vi. This is literally the code inside of your error ring if you've ever wondered how it works. Well, you probably haven't because you didn't know what an X node was, but now that you know what an X node is, and you know an error ring is an X node, this is the generated code inside of an error ring X node. So this X node was causing the active framework PPL to become corrupted. So we've got PPLs, we've got classes, and now we've got an X node. Oh my goodness. We are at a severe risk of LabVIEW attacks. We've got 3 of these problematic features all working together against us. So what did we do? How did I help the LabVIEW programmer? Well, first of all, we removed all of his X nodes from his PPL source, and that included the error ring that I showed here. But he also had in his code, there were places in his PPLs that he was building where he was calling match regular expression. which, as you know, is an X node. And so he was finding that even that was causing crashes with his control F. So then he went through that code, got rid of the match regular expression. There is a VI analyzer test that can help you find all the X nodes in your code. He replaced them. And once he got rid of all the X nodes in his hierarchy, the crash no longer occurred. Control F worked just fine. The developer is officially unstuck. In my opinion, if you can't use Control F in LabVIEW, you are stuck. Your entire team has to remember throughout the course of an 8-hour day, don't ever press Control F when you're doing actor framework PPL stuff. In my opinion, that is a stuck situation. So I'm glad we got him unstuck. We got a couple of bugs filed to R&D. One of them was the simple one, get rid of the error ring in actor framework. And there's a follow-on bug that was basically figure out why when the PPL has an X node in it, Control F doesn't work. So my recommendation going forward is do not use the error ring if you're writing code that is going to be built into a PPL. More generally, just don't use the error ring because it's an X node, and who knows what other kind of problems it might cause. All right, so let's talk about another feature in LabVIEW that I like. I used to like the error ring, like I mentioned. Well, another thing that I like is class property nodes. I love class property nodes. In my opinion, the property node syntax makes any LabVIEW block diagram easier to read because text-based info within a graphical program greatly improves readability. And you know, that's saying something coming from me. I'm the LabVIEW guy, right? And I'm telling you, if there's more text on your block diagram, it's probably going to become more readable. You are never going to convince me that the code on the right is easier to read than the code on the left. Not only is the property node syntax extremely easy to read, we can instantly tell what properties we're setting in our class, but also it takes up way less space. And we're not trying to cram textual information into these 32 by 32 pixels that are part of an API that we regularly use. We've got the drop-down syntax on the property node, way better with the textual information than the access or sub-VI calls. So I promise this is going to be related, but now let me switch gears and talk a little bit about coercion dots. Now, if you've ever heard me talk about coercion dots, you've probably heard me talk about how much they pretty much don't matter. For example, we've got, we're indexing out of an array with a U32. Totally not a big deal. Coercion dot means nothing. It's not helpful at all. We've got a variant terminal that we're wiring anything but a variant into. This is the DQMH in QVI. We can see we're wiring in a cluster of information to that variant terminal. Totally not a big deal. Whenever you've got static dispatch class terminals and a child class is wired into that terminal, you'll get a coercion dot. Totally not a big deal. But oh my goodness, if you see a terminal on a class property node or coming, you know, of a wire coming out of a class property node that has a coercion dot on it that is a type def, oh my goodness, watch out. You are definitely going to have some problems down the road. Let me demonstrate this. So I'm going to open this project. And this is a very simple project. Close these VIs to give us a little bit more stuff on our screen or clearance on our screen. So we can see here that we've got a class property node with a couple of properties, including one that is a type def cluster. Okay. Now I'm going to go in and I'm going to make a change to this type def. Now, the purpose of this demo is to describe the problems with coercion dots on these terminals. There are a bunch of ways you can get the coercion dot, things like saving the type def with a different name or moving it into another library or a bunch of other stuff. I'm going to show you the simplest way that I have to make this coercion dot thing come, and that is to change the type def between strict and non-strict. So it was strict. I'm going to save it as non-strict. And now we can see if we look really closely, we can see that that terminal has a coercion dot on it. Now that's kind of strange, right? Because the accessor VI should have the type def on its con pane, and it's wired to the same type def indicator here. We should not see a coercion dot. Well, things get weirder because if I create a new indicator off of this terminal, we can see that when creating an indicator off of the terminal, we get a coercion dot. That makes no sense. We just created an indicator of the type def that we're wiring the type def to the type def. How can there possibly be a coercion dot? Well, on its surface, this doesn't seem like that big a deal because the code is going to run. The code runs fine. But what's going to happen possibly is that when you go off to build this code into an exe or a PPL or whatever, out of nowhere, you're going to start getting like search dialogues for things that don't even exist anymore. So this coercion dot is basically a clue to you that something bad might happen down the line. Now, getting rid of that coercion dot is hard. Like if you force recompile the VI or if you close LabVIEW and reopen it, the coercion dot's still there. I have found one way to get rid of that coercion dot, and that is to open the accessor, to disconnect the terminal on its COM pane, and then to reconnect the terminal on its COM pane. And when you do that, the coercion dot goes away. So if you ever see this ludicrous coercion dot on terminals that should not be there with class property nodes, definitely take it seriously and fix it in the way that I just illustrated to avoid build issues down the road and possibly like search dialogues when you mass compile your code or anything like that. So I still love class property nodes. See, error ring, it's dead to me. Class property node, because I have an easy workaround with error ring. I could just use error cluster from error code. That VI is super easy to use and it does pretty much the same thing as error ring. So I've kind of switched over. But class property nodes, I love them so much. I have not given up on them. I'm okay with the workaround of going, that ludicrous workaround of disconnect, reconnect to get that coercion dot to go away. We filed some bugs on these things to LabVIEW R&D. Some of them have been fixed. Some of them have been deferred. For now, I'm going to keep using class property nodes because I still love them so much. I'm going to glance at the chat real quick because I've been talking so much. I want to see if there's anything anybody's asking. It looks like Derek's talking about how search doesn't work on the text in an X node. That is correct. There is a post on the idea exchange about getting find to work on error ring text. Obviously, it hasn't been implemented still in the idea exchange. And then, somebody was asking about the technology for malleable VIs. Matt's right. They used to be X nodes. They are now, I think, malleable VIs use instance VI technology under the hood. So malleable VI is using a similar instantiation technique that Express VIs use, I think. All right, so I think that covers some of the stuff y'all were asking. I apologize if I missed something. I'm going to keep going. Oh yeah, and one last thing. If anybody ever gives you crap about wanting some text on your LabVIEW block diagram, just tell them to talk to me. Because a graphical program, I love programming in LabVIEW. Graphical programming is the greatest, but there are just simply some things that are easier to understand on a block diagram that help you understand them faster, and property nodes are one of those things. All right, let's talk about Act 2, which is App Builder Checkbox Roulette, which is officially the second worst kind of roulette you could possibly play. So has this ever happened to you? You've got code in LabVIEW that runs and it works just fine in your IDE, but then you go to build an EXE or a PPL and you get your build breaks. You get an error during your build saying that there's a VI that's broken in your code, even though all your VIs seem perfectly fine in the IDE. Or maybe your EXE builds, but then when you try to run it, it's got a broken run arrow, or you start getting search dialogues. If any of these things have happened to you, you might just be the next contestant on Checkbox Roulette. Come on down. But hold on. Before you come on down, let's see if we can avoid having to do Checkbox Roulette in the first place. Because again, it is the second worst kind of roulette you can play. So before you play App Builder Checkbox Roulette, mass compile your code. There are two ways to mass compile your code in LabVIEW. The first is in the Tools menu, Tools, Advanced, Mass Compile. The second is by right-clicking on the top-level object in your project, and you'll see an item in the project right-click menu for mass compile. Don't use the one in the project. I do not trust it. There's times where I try to mass compile my project from that thing, and it just goes for hours and never finishes. And then I use the one in the Tools menu, and it finishes in like 3 minutes. So just don't use the one in the project. I don't trust it. But yeah, mass compile your code if you can. Another thing that can definitely cause issues with App Builder is if you have conditional disable structures on your block diagram, and the runtime engine equals true case has like a broken wire in it or a broken sub VI or something like that. Well, that code doesn't run when your code's in the IDE. So you run it in the IDE, runs, works great. But then when you build the exe, that broken code in the RTE frame gets activated in your exe break. So make sure there is not any broken code in a conditional disable structure runtime engine frame. I've seen that a bunch. Keep an eye out for that. Now, there is this really cool tool in LabVIEW 2019 and later called Find Broken VIs in Project. I give you the path there on the slides. That VI, you can point it at your project. Let's say you've got an exe that takes an hour to build, or 2 or 3 or 4, hopefully not too much more than that, but you've got an exe that takes a really long time to build. Before you kick off the build, run this VI. I guarantee it'll only take a few minutes to run. And if there are any broken VIs in your project, it will tell you about them, and you can try to address those before you even try to kick off the build. And then, yeah, about once a year, I run into a situation where things are just weird in LabVIEW. Like the VIs, you know, they're runnable, but then the exe breaks or whatever. And the way I fix those issues is clearing the compiled object cache. So that's another thing you can try before you play App Builder Checkbox Roulette. Go clear the compiled object cache, mass compile your code again. I know it's a pain, but I'm trying to get you so you don't have to play Checkbox Roulette. If none of those things work, and then you're on the latest LabVIEW with all the latest patches, we're pretty much that's our last straw. We pretty much have to play App Builder Checkbox Roulette. A question in the chat: does the find broken VIs get called in the preview check in the App Builder? It does not. App Builder does have things that check your code for broken stuff that does run as part of the preparation step. The find broken VIs in project, I think, I don't know why it's not used in App Builder, but I think I was told there's a reason that it's not used in App Builder. So it's kind of like a sort of a, you know, here's another tool in your toolbox sort of thing. All right, so App Builder Checkbox Roulette. These, basically what it boils down to is you go into App Builder when your exe won't build, and you start just clicking random checkboxes and trying to build again to see if it works. That's App Builder Checkbox Roulette. I've included the 6 most common checkboxes that I've seen that cause builds to work here in the slide. The first one is enable debugging. That is going to make your exe balloon in size. So maybe your exe was like 5 megs before, and now it's like 50 megs when you enable debugging. But you know, if you're trying to get unstuck and you're looking for a workaround, that's the first checkbox I would turn on. Enable debugging, see if your build works. Then going down from there, we've got the other options that you can go mess with. Most of them are on the additional exclusions page in App Builder. Also, I recommend that you should always check the option to exclude dependent PPLs. And the reason I recommend that is because I also recommend that PPLs always be in the same spot on disk. So if your PPLs are always built to and installed to C:/PPLs, then your exe is never going to need to include them because it's always going to point to that spot. So hopefully, if you follow my previous recommendation of always building the same spot, you can check that without having to worry about anything else. So, but, you know, Checkbox Roulette, it might not fix your issue. And if it doesn't, I mean, at that point, you pretty much have to contact NI support, right? Well, I propose that if it does fix your issue, I'd still like for you to contact NI support and, if possible, share the code with us so we can file a bug to R&D about this issue, this build issue you had that was fixed with App Builder Checkbox Roulette. We need bugs filed against App Builder to make it better. App Builder gets better with every LabVIEW release. LabVIEW R&D fixes bugs, but we need those bugs to get reported to us. And in my opinion, one way to possibly not have to play App Builder Checkbox Roulette in the first place is to avoid some of the problematic features that I've talked about in this presentation. All right, so looking at the chat, I think we're good. Somebody mentioned shared variables. I don't know anything about those, so I'll just assume Matt Jacobson's got that one covered. All right, so Act 3. LabVIEW is a parallel language, right? Right? Well, we're certainly taught that on day 1 of LabVIEW Core 1, where, you know, we're shown block diagrams. Maybe they don't look like this, but some representation of LabVIEW being a parallel programming language. You know, once all that initialization code on the left runs there, then those 3 loops in that event structure can all execute in parallel. Well, it turns out that the assumption that LabVIEW block diagrams always execute in parallel is not a perfect assumption. So let's get back to LabVIEW. We're going to open up another demo project here. And in this project, I've got some code that is calling the Python node. So the really simple block diagram, we're calling a Python node, and we are checking to see how long it takes to execute. And here, we'll throw that one out because that was the first run. It was having to load everything in Python in memory. So here, if we run a couple times, we can see, oh, all right, it takes about 1/4 of a second to run. Well, I've got this other VI that is exactly the same thing, only we are running 4 instances of the exact same code in parallel. So if we run this VI, we see that it takes about 4 times as long. So the first one took about 1/4 second, and the last one takes this one takes about 1 second. So my conclusion from seeing that is that the Python node is unable to run in parallel. There must be some shared resource having to do with calling Python that those Python nodes need access to, so they have to run serially. Well, that was my assumption when I saw this code, but there's this knowledge base entry here about executing parallel processes with the Python node in LabVIEW. Huh, well, that's interesting. That's exactly what I thought I couldn't do based on running that code. So if I scroll down, words, I'm going to read this paragraph out loud. The following is an example of calling 2 Python functions in parallel using 2 separate Python sessions. Note that the while loops are set to terminate after just 1 iteration. However, this instructs the compiler that these 2 processes should run in parallel. What are they talking about? There is no reason you should have to wrap code in a dummy loop just to make it run in parallel. Also, while we're at it, why is one of these your function 1 and one of them your function A? That's super irritating. So one of our TSEs brought this knowledge base entry to my attention, and I said, oh, well, that's obviously wrong. Like that, wrapping your code in a while loop just to make it run in parallel, you don't have to do that. LabVIEW doesn't work that way. This knowledge base entry is wrong. Go fix it. But then before I told them to go fix it, I thought, you know what? Maybe I should actually try this first. So let's try it right now. I'm going to wrap these guys in while loops that only run once. And then I'm going to, so we got the while loops. Now I need to tell all of them to run once. So this is what that knowledge base entry was telling me. And holy crap, now they're running in parallel. I could not believe that this happened. And now you can see why that knowledge base entry is still there, because it is conveying correct information. So why did this happen? To answer that, we're going to need to talk about clumps. Now, you may not have ever heard the term clump as it pertains to LabVIEW programming. Even if you have heard the term clump as it pertains to LabVIEW programming, I have a homework assignment for each one of you watching this presentation right now. And that is to go to Google and search for LabVIEW compiler under the hood. This is one of the best articles on ni.com, which I know is probably not a terribly high bar, but I promise this article is worth your time. It is so worth your time. I recommend making a calendar entry to reread this once a year. I reread it a couple of weeks before I gave this presentation back in July because the information is so useful to keep in your back pocket for when a more detailed understanding of how the guts of LabVIEW work is in order. All right, so when you read that article, you are going to find out what a clump is. I'm going to summarize it here. Whenever you have a LabVIEW block diagram, there are various levels of intermediate representation that the compiler takes your block diagram through before it ends up with actual compiled code. And one of the things that happens when the intermediate representation of your block diagram is created is that nodes on your block diagram, or their representation of those nodes, are grouped together into what are called clumps. And a group of nodes in a clump, that is basically LabVIEW, the compiler's way of saying, this group of nodes can run in parallel with other groups of nodes that don't have data dependencies. That's what a clump is. So if the LabVIEW compiler can figure out, all right, well, this part of the block diagram, it can all run on its own. This part of the block diagram, it can all run on its own. Oh, so these two could run in parallel, basically, is what clumping does. Now, it's my understanding that most nodes in LabVIEW have an internal flag on them that tells the compiler, you know what? It's okay for this type of node to start its own clump. So this type of node can be in a parallel executing part of a block diagram. For example, while loops have this flag, which by association is going to be applied to all of their contents. So anything, a while loop and all of its contents can be turned into a clump. The Python node does not have this flag currently. So the LabVIEW compiler sees a Python node and it basically says, this guy, he cannot run in parallel with other things. He has to be serialized. So if you've got a block diagram full of Python nodes, each one of those are going to be serialized because they're not allowed to make their own clumps. But remember, a while loop creates its own clump for all the stuff that's inside of it, which is why that ludicrous trick actually worked to just wrap those Python nodes in a single iteration while loop. So clearly we have illustrated through the demo I just showed you that there's no problem with a Python node running in parallel with another Python node. So I filed a bug to LabVIEW R&D that Python node should probably get this flag to let them start their own clumps. And it's my understanding that this bug is going to be fixed in a future LabVIEW version. So this is one of those things where we got the bug report into the TSE group. We came up with a ludicrous workaround, which is shown in that knowledge base entry. But we were able to take that information, pass it to R&D, and get the product to be made better as a result of this bug being filed. So definitely share this stuff with NI when you can. So let me double check the questions. Did we try putting an always copy node before the Python node? We didn't. Based on my understanding of the scenario, that wouldn't work because, again, we're falling back into the Python node doesn't have that clumping flag set on it. So I don't think an always copy would help with that. We could certainly try it and see if it would. But at the end of the day, when I just wrapped that code in a dummy while loop, I felt like I was smacking the side of LabVIEW to try to make it work better. That's ludicrous. We shouldn't have to do that. Not with this programming language. All right, Act 4, the final act of my ludicrous play. The answer to the ultimate question of life, the universe, and everything, it's not 42, it's 24. Here, I'm going to show you. So we've got another case study. It's another active framework case study. And what we were seeing was that we had a DAC application that was calling, I'm going to just refer to them as DAC actors. They are actors that were wrapping some DAC functionality. And when we had 23 of these DAC actors or less running, everything was working great. The moment we spin up the 24th DAC actor, all the messages between all of the actors started slowing down. Not just this new actor, but everybody's messages started slowing down as soon as we spun up that 24th DAC actor. Now, looking at the code in these actors, they were calling DAC-MX read. Again, remember I mentioned it, the DAC actor is just a wrapper for doing DAC stuff. Now, DAC-MX read, we thought, well, okay, is it a hardware issue? So we decided to try it with simulated DAC devices, and the problem still happened. So real hardware, simulated hardware problems still happened. If we replaced the DAC-MX read calls with something simulated, just some random number generator or something that just simulated the data, the problem went away. And when I heard that, I was like, oh, thank goodness, it's a DAC issue. I don't have to worry about it. I'm the LabVIEW guy. But then hold on, wait a minute. I realized my reaction was too swift. Remember, my goal is to get people unstuck, right? So I'm going to see what there is that I could possibly do on this on the LabVIEW side, right? Because regardless of any issues with DAC, I found it very strange that it was always exactly 24, like always the 24. That never happened where they were like, oh, well, this time it was the 22nd one that caught. Nope, it's always the 24. Well, actors are reentrant by definition. DAC-MX read is an inline VI, so it's basically, the DAC-MX, there's the sub VI border isn't even there when the code's running. Clearly, there is a DAC issue, right? Because when we tried simulated data, the problem did not happen. But I was curious, is there something on the LabVIEW side that was imposing a limitation on the number of parallel threads that could be spun up? The answer to that question is yes. So this is my LabVIEW log file. If you ever want to see a whole bunch of really crazy stuff about what's going on while your LabVIEW is executing, go into your temp folder and find the file called LabVIEW _ bitness 32 or 64 _ version _ username _ log. There's also a file that's _cur at the end, which is the current LabVIEW that's running. In this file, you're going to find all sorts of crazy information about what's going on behind the scenes when LabVIEW is starting up, while your VIs are executing. And one of the really curious things I found in this file was that it added a line every time a new thread was started up in a LabVIEW execution system. And goodness gracious, every one of those execution systems has a thread capacity of 24. 24 is the exact number of DAC actors that were being spun up and causing an issue. Well, what in the world is this stuff talking about, okay? Execution systems. If you go into the VI properties of a VI, you'll see the preferred execution system drop down, and you'll see different execution systems like user interface and standard and all those. Well, it turns out that LabVIEW is going to spin up a maximum number of threads for every execution system in the LabVIEW executable while it's running. And LabVIEW has a heuristic to determine what the capacity of threads is for each execution system. But by and large, on most systems, regardless of OS or hardware, that value is almost always going to be 24. It's not affected by like number of processors or whatever. It's almost always 24. But you can override that value with an INI token. Exec thread grow capacity equals number. Again, by default, it's 24. On the LabVIEW programmer's system who was having the problem with these DAC actors, when he bumped that number from 24 to 48, which we just kind of arbitrarily decided, let's double it and see what happens, it completely fixed the problem. Everything on his system started running great. No more delays with his actor framework messages. It was just an instant fix. But I wasn't terribly happy with that fix, because what if there's a point where he adds another compact DAC to his system and now 48 threads isn't enough? What's he going to do? Bump it to 96 and hope that that works? That doesn't feel scalable to me. What if, yeah, there's not only the DAC actors, but now he's got other threads being spun up for some other feature of his application. I felt it was important to figure out why this why we were hitting the thread capacity in the first place. And so I set out to discover a tale of two settings. This slide, even though we have 3 minutes left, is the most important slide in my presentation, I think. So pay careful attention. Reentrant VIs like actor framework actors or DQMH clonable modules. When a VI is reentrant, your operating system is responsible for taking those threads, putting them to sleep and waking them up whenever threads access a shared resource. Remember, with our customer scenario here, the DAC driver had some sort of shared resource we hadn't identified yet, okay? So the OS is taking a thread, putting it to sleep, waking up another thread, then re-waking up that previous thread. OS is responsible for that. When VIs are non-reentrant, the OS isn't in the picture. The LabVIEW execution system is responsible for basically ordering the serial operations. So if you've got non-reentrant VIs, LabVIEW is going to say, all right, we're going to run this one, then this one, then this one, then this one. LabVIEW execution system figures out all of that stuff. It is incredibly highly resource intensive for your OS to switch between threads. It is much less resource intensive for the LabVIEW execution system to serialize non-reentrant operations. So much so that in rare cases, like the one in this use case that we've been talking about this whole time, a non-reentrant wrapper VI around a reentrant VI accessing a shared resource is actually more efficient than if we had just left everything reentrant in the first place. We were able to prove this. So remember, the customer system, they solved the issue by bumping the INI token. Well, I took the in-house system we had at NI that was reproducing this issue, and I put a wrapper around DACMX read. I just wrapped it in a non-reentrant sub-VI. That's literally all I did. And when I did that, that also solved the problem in half the number of required threads. Remember, I could do this because DACMX had some sort of as yet unidentified mutex. DAC had an issue. We were trying to work around it. The customer system, they worked around it with the INI token. I worked around it by putting a non-reentrant wrapper around the DAC call that had the mutex. My fix used half as many threads, and we still got the performance on the system. So in my opinion, the non-reentrant wrapper on the shared resource is the better solution because it scales. Even once we start spinning up some more things, we don't have to worry about the thread capacity. Okay, perfect. 1 minute for me to tell you guys, nobody loves LabVIEW more than I do, except maybe Jeff K. I'm willing to give him that, all right? I want LabVIEW users to be successful and not stuck, and I want y'all to go home happy after programming LabVIEW after a day's worth of work. Sometimes we can get you unstuck in ludicrous ways. I can try to help with that with things like this presentation and more resources built upon it. Sometimes you can avoid getting stuck at all by avoiding problematic features in LabVIEW, like PPLs. Please avoid PPLs if you can. Thank you for attending my GLA Summit presentation. Finished right on time. Thank you, everybody, for the claps and applause. I can stick around in the chat for a couple more minutes. Aaron, it seemed like you wanted to mention something. Christian, how do the Visa nodes relate to shared resources for different Visa resources? I am not a Visa guy. I do not know the answer to that question. Thank you, Chris. You guys got another presentation to head off to. But yeah, if y'all want to stick around for a couple of minutes, I'm happy to answer questions or talk to any of the topics that were brought up in this presentation. A question about why is the OS management of threads worse? Because whenever you have reentrant VIs that are being swapped between, that is the OS swapping threads. There's actually not thread swapping when the LabVIEW execution is serializing non-reentrant VIs. So like at that point, you're not dealing with thread swapping. You're dealing with the LabVIEW execution system saying, I'm going to execute this non-reentrant VI, then this one, then this one, then this one, then this one. That's all happening in the same thread. So when you turn a reentrant VI non-reentrant, if there is no shared resource, you're probably going to hurt your performance because now things can't run in parallel. But if there is a shared resource, now you've taken unnecessary thread swapping that the OS is doing and just letting the LabVIEW execution system serialize things. All right, what else? Just scrolling back through the chat to see if I missed anything. Matt's asking about INI token causes LabVIEW to start the max number of threads immediately. I don't think that's true. So we saw, I believe LabVIEW decides a certain number of threads to spin up per execution system. I think we saw in my INI, or I'm sorry, in my log file that it was 8. Sorry, I'm doing slide magic here. Yeah, so we can see that at the normal capacity of 24, it spins up 8 threads, and then it starts spinning up more if it needs them to get up to the capacity. I don't know if you bump it up to 48 if it like starts up 16. I don't think it does. I think by default it spins up 8, and then it spins up some more if it needs to. Let's see. If you have to clear the object cache often, what is that a symptom of that should be avoided in the code? It's a symptom of bugs in LabVIEW. So if we can, there should be no reason that we have to ever clear the compiled object cache. It is becoming stale or getting bad info in it because of a bug in LabVIEW, which we hopefully can get those fixed. Sam is trolling me with the question of why avoid PPLs. Clearly, he did not watch my presentation, or he did and he's trolling me. Definitely watch the recording. They are the #1 most common support issue, or the #1 most common feature of LabVIEW and support issues that I worked on over the past couple of years. So I suggest avoiding them to avoid the support issues they bring along. David asks, are polyVIs a good replacement for malleables? In my opinion, as I mentioned in the presentation, I would prefer to have a clunky API than risk malleable VI build issues. There are some pathological poly VIs, like some of the OpenG ones that have like 30-something instances. I make a lot of poly VIs in the projects that I work on, actually, but I don't make them like, I don't make poly VIs for U8, U16, U30, and like all the numeric types. Like I'll make a poly VI that's got like a I32 instance and a double instance, and I'm okay with the coercions on the non I32 and double types. But yeah, but there are cases where if I wasn't scared of malleable VIs, I would implement VIMs, but instead I implement poly VIs with a limited number of instances because I just want to avoid the malleable build issues. Let's see. Anybody else? Let's see, Aaron, I think you said you wanted to ask me something. I'm not seeing a question from you yet. Matt says clear cache when switching branches. I know some teams that clear the cache on every build. Like part of their exe build process is clear the cache. Like their pre-build VI clears the cache and then they build. That they must have run into some pretty bad build issues to have to do that. Aaron, if you want to like send me an email, if it's about the, I remember somebody asked me something about the bookmark manager. If it's about that issue, I think somebody's handling that, but you can send me an email if you want to discuss it further. Let's see. Derek's mentioning version control stuff. I feel like a lot of the compiled object cache issues I've had probably aren't related to Git. Again, I fall back on LabVIEW just not handling like file timestamps correctly and other stuff too. Yeah, I've definitely run into weird issues where like I've got a VI and it's got a broken wire on its block diagram, but if I give that to somebody else and they open it, there's not even with malleable VIs sometimes. They open it and there's not a broken wire, and it's just because the compiled object cache got weird and it didn't realize it needed to update. Let's see. All right, Aaron, I'll check with the TSE tomorrow who's working on the bookmark manager thing and see if he needs any help or if I need to step in any way. I have also seen some bookmark manager errors. Like I got a very brief description on the problem that you're having, and it sounds somewhat familiar to me. But I can look into it. I can check in with them tomorrow and see what's going on. It may just end up being a bug getting filed to R&D. All right. Any last questions or comments before I get out of here and collapse after giving 3 presentations today? Do you know what the could not save bad VI without block diagram error is when compiling? Sounds like, assuming you mean compiling VIs and not like building an exe. EXE, yeah, that's an app builder checkbox roulette situation right there, or a compiled object cache clearing situation, or a bug in LabVIEW that we need to get filed. Well, I mean, it's most definitely a bug in LabVIEW, but in terms of trying to work around those types of issues, app builder checkbox roulette and clearing the compiled object cache are the things that I like to try. Also, there's the app builder cache that you can clear as well. All right, anything else? All right, everybody, I think I'm going to call it. Thank you for coming to my presentation. And remember, this and all the other stuff that I talked about today and all the other presentations that I've given are all at dnat.org. So definitely check that stuff out there. Yeah, thanks everybody for attending. We'll catch you on the other side.